All right, everyone. It is great to see you here, and welcome to this edition of Rocky World's discussions. Are we recording? Yes, perfect. Right, okay, so very pleased today to welcome Josh Krissansen-Totton, who joins us from Washington today. And as a reminder of netiquette, we invite you to use your full name and keep muted throughout the talk. And please turn on your video on at the end, if possible, when asking questions. So I will stop sharing my screen and now hand it over to Josh, who will tell us about the case for secondary atmospheres on temperate planets around M-dwarfs.
Thank you so much for that introduction and for the invitation to speak today. Okay, hopefully this is all working now. So yeah, this is perhaps going to be a bit of a controversial and one-sided argument. Obviously, we don't know the answer to this question, whether temperate rocky planets around M-dwarfs have atmospheres. This is a question that will be answered observationally. But I, at least, in the spirit of generating some good discussion, I wanted to present kind of the optimistic case here to you today, and yeah, be very interested to hear your thoughts and feedback. So, beginning a talk with a complicated looking table like this is probably a terrible idea and something I would tell my students not to do. But this is actually something I use in teaching classes. It's a table of rocky exoplanets for which we have decent constraints on whether or not they have atmospheres, and I find presenting it as a table is a nice way to kind of capture the multidimensionality of these of this sample of planets. So you'll see here I'm just listing their mass, their radius, the bolometric installation they receive relative to Earth, the stellar type, and whether or not they seem to have substantial atmospheres based on observations so far. And so, with a few exceptions that we'll talk about later, at a quick glance, this is pretty bleak, right? A lot of these objects that we've looked at so far, thermal emission observations with JWST, don't seem to have substantial atmospheres. But it is really important to note that when you look at the bolometric installation received by these objects, for the most part, these are really hot rocks. These are not true Venus analogs. These are things that receive installation comparable or much greater to Mercury. And this is also reflected in sort of cosmic shoreline plots. So this is, of course, based on the Zarnley and Catling paper. This is Nick Wogan's version of the cosmic shoreline. And just to remind you what we're looking at here, the cosmic shoreline is a sort of quasi-empirical relationship that separates objects in the solar system, at least, between those that have atmospheres and don't. And there are different forms of it based on sort of different underlying physics for atmospheric escape, but this is plotted in terms of the cumulative XeV received by these objects, with the assumption that that is potentially driving a lot of hydrodynamic escape. And then on the x-axis here, we have the escape velocity of those objects. And in this version of the cosmic shoreline plot that Nick has put together, he's color-coded these objects by whether or not they have atmospheres or substantial atmospheres based on largely JWST observations. And so you can see there are a bunch of planets up here that don't have atmospheres. So this seems to be bad for these hot rocks. But the question I want to think about today is, given these observations so far, what are the prospects for the more temperate rocky planets around M-dwarf planets, which are, of course, of interest for habitability? What, if anything, do the observations so far of hot rocks imply for the more temperate cousins. So this is kind of a three-part talk. The first part of it, I'll present some work on atmosphere interior evolution models that makes a case for why these objects might hold on to secondary atmospheres. And this is kind of be the work of my research group. And then the second two parts of the talk, I'll talk about some other literature on escape models that perhaps suggest the same thing. And at the end, perhaps some sort of tentative observational evidence for atmospheres that might support this story. Okay, so some important context for what follows. Something that we've learned from population, demographic studies of exoplanets is that many or perhaps most rocky planets formed with a large primary atmosphere. And this comes from this sort of bimodal planet size distribution that I'm sure you've seen before in some form. There's obviously ongoing debate over the origin of this bimodal distribution, but in my mind, kind of the simplest explanation of this is that, all of these objects, or many of these objects, are started from the same volatile-rich population with a lot of hydrogen, and then some of those had their hydrogen-rich envelopes eroded to become genuinely rocky. Can you see my cursor, by the way? Is that showing up?
Yes.
Okay, great. So the implication of this being that many of the now rocky planets that are out there began their evolution with substantial, hydrogen helium envelope. And this is quite different, we think, to Earth's evolution. Earth did not seemingly possess a long-lived large primary atmosphere, and there are various lines of evidence for this that I won't get into now. But accepting that this is true, it kind of raises an interesting question. If Earth is a bit weird in this way, and that it, rather than getting its volatiles from a large primary atmosphere, it kind of accreted them from chondritic material, what might be the implications of losing a primary atmosphere for all these other rocky planets that are out there? So how does beginning a revolution with a substantial primary atmosphere affect the subsequent prospects for atmospheric retention and, of course, habitability, since this is perhaps a lot of the habitable zone real estate that is out there is rocky planets that formed with a large primary atmosphere. We want to know how that affected their later evolution. Okay, so to tackle this question, there are not kind of off-the-shelf models that you can use. A lot of the evolutionary sort of magma erosion models that have been previously used to understand terrestrial planets are sort of limited to more oxidized atmospheres, water and CO2, and maybe oxygen, so secondary atmospheric compositions, based on the fact that Earth's mantle is fairly oxidizing. There have been in the last few years a few really interesting attempts to kind of generalize magma erosion models and incorporate a greater diversity of atmospheric compositions, including more reducing compositions that could accommodate, a hydrogen-rich early atmosphere. For the most part, these models haven't allowed for evolution, though. I will say in the last few months, there have been a few exceptions to this. A few really interesting new papers have came out that do allow for a more general range of atmospheric compositions and allow those to evolve with a magma erosion model. And so I'm excited to do some comparisons with these models in the future and see if we can reach some consensus on how these objects evolve. But here is kind of our take on the problem. So how does a long-lived primary atmosphere affect the subsequent atmospheric retention prospects for rocky planets? We attempted to build an evolutionary model that would capture the atmosphere, the magma ocean interior, and their interactions. So there's a lot of competing effects when you try and answer this question that we tried to capture with this model. Of course, you potentially have a lot of atmospheric loss, particularly around stars that are very active in the XUV, and so this can drive a lot of hydrodynamic escape of hydrogen, and then that escaping hydrogen can drag along with it heavier atmospheric constituents, oxygen, carbon-bearing species that could potentially, strip your planet of all secondary volatiles and leave it like a bare rock. So we need to capture this escape process. And without getting too much into the details, we try and incorporate, the evolving bolometric luminosity of the star, as well as its evolving XUV. So these are time plots here, the envelope of evolving XUV luminosity, given all the uncertainties in stellar evolution, and calculate how that drives either hydrodynamic escape or diffusion limited escape. So that's the escape side of things. But of course, if you have a substantial atmosphere, the planet is very, very hot, and so you have a molten magma ocean where you can dissolve volatiles into the interior, potentially shielding them from atmospheric escape. And so we calculate how hydrogen, carbon, oxygen bearing species are partitioned between the molten interior and the atmosphere. And we also try to incorporate chemical reactions between these volatiles and the molten silicate interior. So for example, ion-bearing silicates can react with hydrogen in your primary atmosphere to replenish water and produce metallic ion. And so we try and incorporate these reactions into our model. And this is not a time evolution plot. This is just a bunch of snapshots where on the x-axis here, we're just dumping an increasing amount of hydrogen onto our planet. So this is the mass fraction of hydrogen that we add as a fraction of the total planet mass. And then we're calculating how atmospheric constituents speciate, so the mixture of water, hydrogen, CO2, CO, oxygen, and methane, and total atmospheric pressure as you add that hydrogen. How does the dissolved how do the species in the magma ocean change? And then how does ion speciate as you add more and more hydrogen? Of course, as you add more and more hydrogen, the redox state becomes more and more reduced. So this is just giving you an example of how that equilibrium calculation is done. Okay, so this next slide is a bit of weeds. The details of how we do this, if you don't care about the details of magma ocean models, you can check your emails for a minute. But for those of you that are curious about the details, just to quickly say what's going on under the hood here, we're calculating gas speciation with equilibrium reactions. We have volatile solubility laws to describe how hydrogen, oxygen, carbon-bearing species are dissolved. Try and take into account graphite saturation. All of this is we're imposing conservation of atoms, hydrogen, carbon, oxygen is particularly important, and then ion speciation. And then we, of course, have to relate the ion speciation to oxygen fugacity for both sort of oxidized compositions with its ion 3+ around and more reducing compositions with its metallic ion around. And then at the same time, we are solving for the equilibrium climate states, so balancing outgoing long-wave radiation, absorbed short-wave radiation, and the heat from the convective magma ocean. So this is essentially one giant set of simultaneous equations that we are solving at every time step to calculate how the atmosphere and the interior evolve chemically as the star is evolving and the planet is cooling off. So, okay, so that's the weedy slide done. This is sort of qualitatively what we're doing. The star is evolving in terms of its bolometric luminosity and XUV luminosity, and then we're calculating how the magma ocean solidifies And as species are lost to space and as the star cools off, to try and predict the final atmospheres or lack thereof for these planets. And of course, as you're losing atmosphere, the redox state of the whole planet is evolving. You're potentially getting more oxidized as you lose hydrogen to space. So hopefully that gives you some sense of what the model is doing. Here's an application of that model to, in this case, TRAPPIST-1b, just as an illustration for evolution for a fairly hot object. And in this particular model run, we just give TRAPPIST-1b a 0.1% hydrogen inventory just to see what that does. And sorry, the slide transitions are going to be a bit messed up here, but we're plotting. So just to show you what you're looking at, these are all of these plots have time on the x-axis, and we're plotting how the temperature of the mantle and the surface, the solidification radius of the magma ocean, mantle redox state, and volatile reservoirs evolve over the 8 billion years of the star's evolution. The dashed vertical line is showing you where the magma ocean terminates. The solid is the surface is solidified. And so just zooming in on a few of these plots, what we see is that because the bolometric luminosity received is so high, it's just driving a lot of hydrodynamic escape. And so this is atmospheric composition through time. You lose all the hydrogen, and with it, you strip all your heavier volatiles. And so you get left with a small amount of leftover oxygen that would be potentially vulnerable to like non-thermal escape that we don't model. But essentially, you strip your planet of volatiles. And the same is true for the interior. I mean, you leave a little bit of hydrogen behind in the planet's mantle at the end of all of this, but you basically strip all the carbon from your planet during the hydrodynamic loss phase. So that's the story for this illustrative case. And this outcome of sort of stripping all the volatiles from your planet is something that is consistent with some previous attempts to model this primary to secondary atmosphere transition. This Kite and Barnett paper didn't worry too much about the details of the chemistry, but they did model the physics of this process and essentially arrived at the same conclusion that hydrodynamic loss should drag away all the heavier stuff and leave you with a fairly desiccated planet for hot planets. But what we wanted to think about next was, how does this play out for more temperate planets, something like TRAPPIST-1e? This is the exact same calculation, except now we're doing it for something that ends up in the habitable zone. And because the received bolometric and XCV fluxes are much lower, while you are losing some hydrogen, at the end of the magma ocean phase, you do leave behind a fairly substantial water inventory. In fact, you're replenishing the water through reactions of the hydrogen with the iron oxide molten interior. And so in this particular case, you end up with a few Earth oceans worth of water and tens of bar of CO2, a little bit of oxygen. In part, this difference occurs because once your planet moves out beyond the runaway greenhouse limit, you can condense water out on the surface where it is no longer vulnerable to atmospheric escape. So this is kind of a large driver of the different outcomes between these two scenarios. And similarly, you do retain sizable hydrogen and carbon inventory because of this difference. Okay, so those are just two illustrative cases. What is hopefully more convincing is to repeat this calculation with kind of a Monte Carlo framework. So redoing the calculation integrating over all the uncertainties in stellar evolution and atmospheric escape and atmosphere interior evolution. And this plot is showing you the outcome of that kind of Monte Carlo calculation. This is for TRAPPIST-1e again. On the x-axis here, we just have the initial amount of hydrogen accreted by the planet, ranging from something less than Earth-like all the way up to sort of 1% of planet mass. And then on the y-axis here, we have the total volatile inventory at the surface after 8 billion years of evolution. And then the bottom panel is showing you the constituents of that surface volatile inventory. And so the shaded region is kind of the Monte Carlo envelope. And so what you can see, I should also say, so this red shaded region is a little bit arbitrary, but it's kind of an increasing danger zone for the total volatile loss that you might expect through non-thermal processes like ion escape that we don't model here. So essentially, the further you are, the deeper you are into the red, the more likely you are to totally lose your atmosphere. So what you can see for TRAPPIST-1e is that no matter what your initial hydrogen inventory, you're unlikely to lose, you're unlikely to be in this danger zone. Basically, you're likely to retain a fairly substantial surface volatile inventory. And as you add more and more hydrogen, that hydrogen is able to react with the molten silicate interior and produce a lot of water, which is the blue curve here. So this result is very different to what you get for TRAPPIST-1b, where due to the high volumetric and XUV luminosity, for that same range of initial hydrogen inventories, you potentially do get left with a final surface volatile inventory that is susceptible to total erosion through non-thermal processes. So you're most likely to be left behind with sort of a thin oxygen atmosphere in these cases. And this is, of course, is kind of consistent with what we've been seeing observationally. Thermal emission observations of TRAPPIST-1b suggest a bare rock or close to it, which is kind of exactly what we are predicting. Okay. And I guess I haven't shown examples of other hot rocks here, but the model is similarly predicts these sort of outcomes for other highly irradiated objects. Okay. So one thing you might be wondering is, why is there this U shape here, this non-monotonic behavior? And this is fairly easy to understand in that if you don't have much hydrogen to drag heavier things like carbon and oxygen, it's very hard to get rid of all that carbon and oxygen. And so you tend to leave behind more of an atmosphere for very low starting amounts of hydrogen. As you add more hydrogen, it's easier to drag off the carbon and oxygen bearing species. And so you get left with very small final volatile inventories. But as you add more and more hydrogen, that can react with the molten interior, replenishing water, which sort of adds to your secondary atmosphere and also kind of shields the carbon from escape. And that if you have more water and oxygen around, less of the XUV energy goes into dragging carbon. So that's why you see this U-shaped behavior. Okay, I'm going to skip over this in the interest of time. This is just to show that you can repeat the calculation for other habitable zone rocky planets, Proxima Centauri, TRAPPIST-1f. You get similar conclusions. Okay, so this is kind of the results from that calculation, that for habitable zone planets, the transition from sort of a primary atmosphere to a terrestrial planet via XUV-driven escape, it doesn't preclude subsequent habitability. You tend to be left with a lot of volatiles, and so we illustrated this for TRAPPIST-1e. In contrast, for very highly irradiated objects, the loss of that primary atmosphere does tend to drag with it oxygen carbon-bearing species, and it's much easier to be left with a pretty thin secondary atmosphere that is potentially susceptible to total loss through non-thermal processes. And while we use the TRAPPIST-1 planets as illustrative cases, I would argue that this result is more general and applies to hot rocks and temperate rocks more broadly. And so this work that I've just been talking about was published a couple of months ago. But what I wanted to do now was kind of mention some other literature that potentially supports this view. There've been a few interesting papers in the last few years getting into the details of thermal escape that perhaps come to a conclusion that is consistent with this. So studies of thermal escape under high XeV fluxes. This Nakayama paper from 2022 looks at how atmospheres respond to extremely high XeV fluxes and tries to model the atomic line cooling that affects atmospheric escape, and find that even for very high XeV fluxes for nitrogen oxygen atmospheres, you don't expect an extremely high loss rate. You actually have a hydrostatic structure and fairly modest rates of escape. This Kawamura paper from this year is looking at a different aspect of the problem, focused on water oxygen atmospheres, and found that the shielding that you get from oxygen and the photochemical recombination of these species to basically remove hydrogen before it can escape is also going to help you retain atmospheres even under very high XeV fluxes. And then this Yoshida paper looks specifically at more primary atmospheres, so atmospheres with a lot of molecular hydrogen, and found that even then escape is less vigorous than you'd expect, because you produce photochemical products that irradiatively cool the upper atmosphere and result in much less escape than what you'd expect with just a pure hydrogen envelope. So, all of this, in my mind at least, points in the same direction. So you might ask, well, okay, that's all very well to have that theory, but is there any observational evidence to support this argument that you might hold on to atmospheres on these temperate rocky planets around M-dwarfs? And if you'd asked me a year ago, I'd say no, but there've been a few kind of interesting recent papers that, while certainly are not exactly what we're talking about here, they're not temperate rocky planets, that they perhaps give some more reason for optimism. So this is LHS 1478b, paper by Pruden August and colleagues that came out a few months ago. I was on the archive a few months ago. So this is a hot rock. This is 20 times Earth's installation, but looking at the 15 micron band, the eclipse depth is very much what you'd expect for a dense CO2 rich atmosphere. It's seemingly not consistent with a bare rock, although certainly follow-up observations are needed to corroborate this and make sure this is a robust atmospheric detection. So Renyu Hu had this paper out looking at 55 Cancri. Now again, not a temperate planet by any means, receives thousands of times the installation as Earth. But just the fact that the eclipse observations seemingly rule out, a thin rock vapor atmosphere and are more consistent with a high mean molecular weight secondary atmosphere, show you that atmospheres can be retained even under very high, extreme stellar fluxes, and this is not just a JWST result. This is consistent with some interesting, pre-JWST analyses of this object that also seem to suggest a substantial atmosphere. And then finally, this work isn't published, but this is from Louis-Philippe Coulomb, who's part of a JWST Cycle 2 program led by Bjorn Benecke, looking at potentially volatile rich objects. And so this is looking at TOI 270b, Note that this is not TOI 270d that there've previously been papers on, a sub-Neptune. TOI 270b is in the same system, but it's much smaller. It's sort of 1.3 Earth radii, so very much in that terrestrial regime. Although based on the mass and radius, there's some tentative evidence for a substantial volatile inventory. If you plot the percentage of water by planet mass, it seems to suggest a lot of volatiles, although you can't totally rule out a bare rock based on the current uncertainties. So this was looked at in transit, and I don't have the transit spectrum for you, but this is just showing you a result from inferring the atmospheric composition from the transit spectrum. And while this is still very tentative, and again, follow-up observations are clearly needed, this seems to suggest, a steamy atmosphere without a lot of cloud is kind of the most favored interpretation of those data. And so the reason I highlight these planets is that when we kind of go back to our cosmic shoreline plot with all these red dots, perhaps making us feel a bit hopeless, you can overplot these new objects and this that have some tentative evidence for atmospheres, and they're on the shoreline. So this is perhaps not this is perhaps encouraging for the planets that are unambiguously below the shoreline. 55 Cancri over off here somewhere. It's a very different object, but certainly above the shoreline. And so, if these results hold up, that these objects do in fact hold on to atmospheres, this perhaps might lend some support to evolutionary models that suggest that similar objects like TRAPPIST-1e have also held on to their atmospheres. And there's of course a number of objects that are kind of down here-ish. I haven't plotted their exact positions, but the other outer planets in the TRAPPIST-1 system, the LP899c, LHS1140b, are all kind of in this less irradiated regime where you might expect them to have held onto atmospheres, and so potentially good targets for observations. And then one final table for you. These are not habitable zone objects for the most part, but these are other sort of true Venus analogs that receive installations that are more comparable to Venus, and perhaps also good candidates for rocky planets that have held on to secondary atmospheres. I haven't plotted these exactly either. For many of them, we don't know their masses, so you can't plot them exactly, but these are also potentially good targets for holding on to secondary atmospheres, given these tentative results that we are seeing. So to wrap up, I would argue that both atmosphere interior evolution models and sort of sophisticated simulations of atmospheric escape tend to predict that atmospheric retention is possible for temperate rocky planets around M-dwarfs. And so while we are finding that many hot rocks that receive installations much greater than Venus are airless or close to airless, there is some very tentative observational evidence for atmospheres on some warm planets that hints at a cosmic shoreline that's perhaps compatible with these theoretical predictions. And okay, so this is entirely my opinion now, this third bullet point, but I would argue that given the high potential payoff from detecting and characterizing these atmospheres, as well as the information that they would provide for future missions like habitable worlds, that doing some high-risk transit and eclipse measurements of more temperate rocky worlds is something that we should consider prioritizing. Just to leave you with a final a few questions for discussion then, although I'm very happy to take questions on kind of any of the above. Something that I think is interesting is, what would it imply if all of this was totally wrong? If we go out there and we find that temperate rocky planets around M-dwarfs are all airless, what would we learn from that? Does that mean that they all had to form pretty volatile pore, or are we fundamentally misunderstanding atmospheric escape physics in some way. Something else that keeps me up at night is, how well do we understand non-thermal escape? I showed you this kind of red shaded region as a danger zone, but this isn't based on much. There are a bunch of different estimates out there in the literature for how much escape you might expect to occur over the lifetime of these systems, ranging over a couple of orders of magnitude, depending on what you assume about atmospheric composition. And so potentially non-thermal escape is significant, or not, and it would be nice to have a better handle on this. And then thinking more about the observations, we have this directed discretionary time dedicated to looking for atmospheres on rocky worlds. This is the DET version of that cosmic shoreline. So how do we prioritize targets given these theoretical results? There's an interesting trade-off between going after the hotter targets where you maybe don't need as many eclipses versus something that's much cooler that requires much longer integration times, but is maybe more likely to hold on to an atmosphere. And then, more broadly, how do we allocate JWST time between thermal emission observations that are going to be better for the hot things that are more likely to be airless versus transit observations where you have all the problems with the stellar contamination that we've been seeing. So with that, I will wrap up, and I'll be very happy to have a discussion. Thanks very much.
Great, thank you so much, Josh. That was great. That was a great way to end Rocket Worlds Discussions 2024. And I invite you all to raise your hands in Zoom, but I think I'll take the liberty of asking the first question. So in your Monte Carlo results, you're getting a very narrow range in the final steam pressure, and it was like kilobars almost all the time if you started with this much H2. So I'm wondering if, you don't observe any steam atmospheres in any of these planets, would you conclude that they could not have started with a primordial atmosphere?
Yeah, it's an interesting thought. I would caution that with those intervals are 1 sigma. And so if you plot the full spread of model outcomes, there is more diversity. And it also does depend, you have to make some choices about what you do with the metallic ion that you make when you react hydrogen with silicates to make water. And so that can also have I just showed sort of one case here, but that can also make a difference. And so, yeah, I think that's an interesting thought that maybe you could use non-detections to say something about evolution, but you'd have to dig into it more carefully. Yeah.
Yeah, cool. Makes sense. Jake?
Josh, really great talk. I'm not sure if I missed this, so sorry if I'm repeating myself, but I noticed that your cosmic shoreline calculation is much different to the DDT one. You had some not your curved a bit, and also many more planets in your calculation were on the air side, atmosphere side. What was the difference between these two calculations?
So I would have to refer you to Nick Wogan, who put that figure together for the details, but just to highlight a few of the main things. So on one of them, the x-axis is logarithmic, and on one of them, it's kind of a weird stretched axis. So I think that's part of the reason for the different shape of the curve. And then also the population of planets being plotted is different. For the DDT, I should have mentioned this, so thanks for highlighting it. The DDT plot shows all the targets under consideration. Whereas Nick's plot is more focused on what are the objects that either we have constraints on atmosphere versus not, or there's observations in the pipeline that have already happened and haven't been published. So it's a much smaller sample, and so that's why you see a kind of a difference in the spread above and below the shoreline.
But even so, there's some I've noticed some planets that on the DDT plot were in the no air side, no atmosphere side. Then on your plot, they were actually bumped up to potential atmosphere side. So I was wondering, what is this shift?
There are some, yeah. So there are different versions of the shoreline you can draw. So I would have to check with Nick on exactly what assumptions he made to create that version of the shoreline. Yeah.
Okay, thank you.
Hey, Ray?
Yeah, I have two questions. The first is I couldn't quite tell what surface pressures you have in your primordial atmospheres, but I'm just wondering to what extent we actually know the geochemistry properly for the solubilities at these very high pressures. An awful lot of the experiments have just been done at 1 bar. And the second question is on a completely different thing, so might as well take that one first.
Well, yeah. So, I mean, it's a great point. Like, what do the chemical interactions look like when you have a very substantial primary envelope? We've kind of done the best we can with the solubility relationships that are out there in the literature. I'm hoping we'll get some more data of those sort of high pressure conditions soon that we can kind of improve these model predictions. I will say though that for planets that end up losing their primary atmospheres and that become genuine rocky planets at the end of this process, you can't start with that much hydrogen, or you just can't lose it all, right? And so that limit for the cases we looked at was about so 1% by planet mass was kind of the largest initial inventory you could have and still get rid of it all. And so that means that the pressure conditions, temperature pressure conditions you're dealing with are hopefully not so extreme that, you know, the extrapolations of the 1 bar experiments that we have are hopefully reasonable.
Yeah, Claire, can I ask a second question, or do you want to pass to someone else?
You might as well go for it.
Okay, thank you for the indulgence. Yeah, so you noted all these planets that are actually quite highly irradiated but have retained an atmosphere. And I'm just wondering, is that actually consistent with your model, which predicts that TRAPPIST-1b gets stripped, or was it TRAPPIST-1c? I mean, is this actually indicating that some planets are too good at retaining an atmosphere, and that there may be something missing in the model?
Yeah, I mean, it's an interesting question. It's something that I want to explore, is to like take this model and apply it to this population of hot rocks to see if it tells a consistent story. I think, you know, even for TRAPPIST-1b, like there is a lot of spread depending, of course, on the initial volatile inventory. And so I would expect perhaps a more, you know, stochastic range of outcomes just depending on the conditions of accretion. Even if you understood escape perfectly, there's going to be a range of outcomes.
Great, thank you.
Tobias?
Hey, yeah, that was a great talk. I was wondering, I guess for 55 Tank 3, if we take the cosmic shoreline argument, the reason that it could retain an atmosphere would be that despite its high irradiation, it has also a very large mass and therefore like large escape velocity. So I was wondering whether you also investigated larger planets in your models. Like I guess the TRAPPIST-1 planets are mostly Earth-sized or even a bit smaller, maybe. I could be wrong though.
Yeah, it's a good question, and I almost hesitated to put 55 Cancri on there because it is such a different regime. I would like to, you know, apply these sorts of evolutionary models to those larger objects, but I guess at the moment I wouldn't really trust the results because so much changes as you scale up planet size in terms of the atmosphere interior interactions, and so at least with our model, I would be a bit hesitant to sort of just change the size of the planet and believe the results without, you know, thinking more carefully about all the ways in which a larger planet would affect volatile evolution.
Yeah, makes sense. Thanks.
Any more hands? If not, actually, I will ask another question, if that's all right. So on your plots, Josh, for TRAPPIST-1e, where you're looking at the atmospheric composition over as a function of the amount of H2 it started with, I remember there was like a very sharp transition at one point where you go from basically no steam to kilobars of steam, and I'm just wondering what is causing that, or maybe
The Monte Carlo results.
yeah. If you can, yeah, here, see, like in the blue line, it just increases crazy at like log 21 kilograms. So, do you know like what's the mechanism that's causing that?
So I'm not sure if I have a great intuitive explanation, but the difference in outcomes that you're seeing there are planets where you start with enough hydrogen to generate enough water through reactions with iron oxide that after the pre-main sequence is over, after you have a few 100 million years of hydrodynamic loss, there's some water remaining that can condense out onto the surface. Right? So there's some maximum amount of water that you can lose during that pre-main sequence. And so if you start with less than that, you just kind of lose it all typically. And so you end up with very little final water, whereas you cross this threshold, and of course it's not an exact threshold, it depends on all the Monte Carlo uncertainties, but the larger starting hydrogen amounts, you generate more water than you can lose in those few 100 million years of the pre-main sequence. And so at the end of that, it all condenses out as liquid water or ice on the surface where it's safe from escape, and it just sits there for the rest of the planet's evolution.
Yeah, I see. So it has to do with just how much you lose hydrogen having to do with how much is there. Okay.
I should maybe just, while we're on the slide, and this goes back to a previous question, you can see here the molecular hydrogen in cyan starts to pick up for these very high initial hydrogen inventories. And so that's why we didn't kind of extend this x-axis any further, because for this starting amount of hydrogen, you hold on to the hydrogen, you're left with a hydrogen atmosphere at the end of the evolution, which is not obviously what we see on these planets. And so the argument is that this is kind of the full range of initial hydrogen inventories that are possible.
Right. Is that because you just run out of FeO?
You
stop making water?
No, this is just like how you just can't get rid of all the hydrogen over the lifetime of the system.
Right. Cool. More questions? Okay. I would ask one more final question if that's okay. I'm sorry if everyone wants to keep on listening to me. But so you're looking at this impact of starting a planet with a lot of hydrogen to end up making water. And I'm wondering if there are any very important differences between that scenario versus just accreting ice. And differences, I'm not really sure what I'm asking, if it's like something observationally that you would tell the difference between those, or something about the geochemistry of the planet. I guess you can answer this however you want to.
Yeah, it's an interesting question. This is actually something that the reviewer had a lot of comments about, was what about planets that accrete ice, not hydrogen, which is, yeah, I mean, I guess I would say that the accreting hydrogen case is kind of more pessimistic in a way, because if you just accrete a lot of water, then that's much harder to lose than molecular hydrogen. And so similar volatile inventories that are water would presumably, if anything, be harder to totally lose all the volatiles from your planet. It's something we didn't really look at explicitly, just because when you dump 20% of water by mass onto a planet, it requires a different kind of interior structure model. So yeah, I can't say too much more other than that, but I guess maybe one thing you would, yeah, I'll just leave it there, because beyond that.
Yeah, sorry, it's a difficult question. I don't think we really know, but yeah, it's really interesting. I see another question from Ray.
Yeah. The idea just occurred to me when we were talking about the hydrogen inventory, the initial hydrogen inventory, that 1% is the most you could get initially and still evolve into a rocky planet. So the question is, why don't all these TRAPPIST planets turn into sub-Neptunes? What keeps it from just all acquiring so much hydrogen that they would wind up as sub-Neptunes?
I mean, that's sort of an interesting planet formation question, right? Like understanding the origin of sub-Neptunes and why they all don't just experience runaway growth to larger planets is, at least as I understand it, like an open question. I'm not saying, to be clear, I'm not saying that these planets did start with a substantial hydrogen envelope. We don't really know, but we just tried to sweep out the full range from something that was, Earth-like, chondritic, all the way up to as much hydrogen as you could have without becoming a sub-Neptune.
Cool. Any final questions for Josh? Going once, going twice. Okay, thank you. Thank you again, everyone, for coming, and thanks again for an excellent talk. So in 2025, we have a couple very exciting upcoming talks. We have a double whammy of some solar system bodies with Catherine DeClear speaking in January and Michael Way speaking in February. So hopefully you can all tune in then. And until next time, hope you have a nice holiday.